Last time we were working in section 1.2, we were talking a little bit about patterns. In particular, we had looked at two types of patterns. Do you remember what they are? Very good. Arithmetic. And arithmetic patterns are ones where we add the same value to get to the next term. And we looked at geometric, and geometric terms are ones where we multiply by the same value to get subsequent terms. And we had encountered at the very end of class last time a sequence that was neither arithmetic nor geometric. It was 0, 3, 8, 15, 24. Okay? I know we talked about a few other things, but those were where we kind of left off on. I want to start with that particular sequence, and I want to show you that it has a pattern as well, aside from the general term n squared minus 1 that it gives us. And I want to show you because sometimes you start out with 0, 3, 5, or 0, 3, 8, 15, 24, and they say find the next three terms. And if you don't have an equation kind of perspective to go from, there's still a way to find the next three terms. So I want to start with that sequence over here. So if you were given a sequence, what was next? 15, 24. Thank you. And you find out pretty quickly that multiplying is not going to work, and this one is pretty easy to know that because there's a 0 in it already. You can't multiply 0 by anything and get away from 0. So it's not geometric. And you start looking for if it's arithmetic or not. What I'd like for you to do is to write down what they would actually, or what you would actually need to add to get to the next term, like this. So this is plus 3. What would I need to add to get to 8? 5. What would I need to add to get to 15? What would I need to add to get to 24? 9. What's that? It looks like it, right? Do you see all the odd numbers showing up? And they're all 2 apart, right, Brooke? Yeah, they are. Like if I looked at the 3, 5, 7, 9 and I kind of did the same thing, I get 2s everywhere, don't I? Okay, so the process of doing this process, or the label for doing this process twice, which I did, is called second differences. If, heaven forbid, you had to do it 3 times, what do you think it might be called? Third differences. You guys are smart. Yeah, that's just how it works. But if I've gotten to the point, either in the first differences here or in the second differences, where I recognize the pattern, I should be able to replicate that pattern to find the next 3 values, right? Yeah. So down here at the plus 2, I should be able to add 2 again. So what would come after the 9 if I added the 2 to it? 11. So either because you recognize we're dealing with odd numbers like Brooke did, or whether you recognize that this is adding the 2's, like I said, either of those, we can take 24 now and we can add 11. And what would we get? These are the parts I'm adding in. Let me put it in a red. I would get 35. And then if I did it again, I added 2. What would come after 11 if I'm adding 2? 13. And if I take my 35 and I add 13, what do I get? 48, yes. And if I take, I didn't mean 11 here. 2 is what I meant to write there, my bad. If I take 2 again and add that to 13, I would get 15. And if I add 15 to 48, what will I get? What is it? 63. And if I were asked, and you will be on a couple of homework problems, to find the next 3 terms, I found them. Okay? So first differences or arithmetic, it's the same thing, and geometric are not the only options. Second differences or third differences is another possible option for recognizing patterns. All right, let's talk about some counterexamples. If you remember from last time, counterexample is an example showing something doesn't work. It's counter to what you expected, okay? Shows it does not work. So if this is telling you to find a counterexample, it's telling you to find an example of something that makes the statement false, that makes it not work. So here's the statement. It says, if n is a natural number, then n plus 5 over 5 is equal to n plus 1. So we're looking for an example that says that that's not true. Can somebody give me what they think might be an example of such a number? We just need to pick an n value. 1. 1 will work. Well, one will give me an answer that doesn't work. Yes. So if I did 1 plus 5 over 5, that would be what? 6 over 5. So this is sort of the left-hand side. And then if I did the right-hand side and I did 1 plus 1, that would give me 2. And if I compare these, that is the 2 and the 6/5, are they equal? No, they're not. Now the reality is there's lots of choices of numbers n. Usually there are, not always, but usually there are lots of choices for counterexamples that show something to be false. So you're not usually looking for that needle in a haystack kind of approach, but you are looking to find one that doesn't work. Now, let's think about from the perspective of a teacher. This is a very common, in fact, maybe when you looked at it, you thought it was even true, a very common thing for me to see written in an algebra class on a paper. Okay? If you were teaching 6th, 7th, 8th grade, where you're looking at algebra and algebra expressions for the first time, you could see this written on the paper. Any idea what the student was thinking or why they decided that somehow the left-hand side would in fact equal the right-hand side?
Maybe they thought they could cancel out the 5 and make it 1.
Okay. So maybe they did something like this and said that's 1, and they didn't touch the n. Could you see somebody doing that? I could. Could you see them canceling out the 5s and deciding it was 0? I could. It's another possibility. Lots of good stuff. So what are they actually, misunderstanding? Well, they're actually misunderstanding how fractions work. If you have n plus 5 over 5, it really means you have n over 5 plus 5 over 5, right? We don't usually break the fractions back apart. We usually kind of start here and move up here. Combine them after we've gotten the common denominator kind of thing. But they can certainly break apart the same way they went together. And this, in fact, is equal to 1. But the part that was missing is that the n value never was actually divided by 5 in that misconception. Okay? So there's going to be a couple places, I believe, where you're going to have to look at counterexamples showing why student reasoning doesn't actually pan out, why it doesn't work. All right, I want to show you another fun patterning example, and this one's very visual for those of you who are my visual learners. I am a visual learner. Who's a visual learner? Who would categorize themselves that way? A lot of us. How about auditory learners? Do you guys, anybody an auditory learner? You hear it and you're just going to remember it. Alicia? No? Hearing it? Nobody's an auditory learner. Kinesthetic? Learn by doing? Physical activity things? We've got a lot of you guys, okay? So I have a daughter who's actually an auditory learner. None of you are. She's amazing. She memorizes scripture from hearing it. Like, I don't mean just hearing it once, but like she memorizes it by song. And so the songs get stuck in my head sometimes too. So yeah, we're going to take a look at something that's very visual. These are called figurate numbers. Lots of fun. This is based on visually geometric patterns. So shapes is what it's based on. These are not arithmetic. They're not geometric. They are often represented by dots arranged in the shape of certain geometric figures. Okay, I gotta get my dot big enough for it to make sense. Hang on. Let's try that. Okay, so we're gonna start with triangular numbers, and I'm gonna draw the pattern of the shape, okay? So you start out with one dot, and then I have this arrangement of dots. And then I have this arrangement of dots. I'll do one more arrangement. Like that. Whew, and then I'm going to have to make them smaller. I'm running out of space. Numerical pattern. All right, so we'll get to the numerical pattern in a moment, but do you see how you would create the next figure? What would you do? Okay, so you're going to add a row to the bottom. I agree. How many will be in the row? 5. One more than the row before, right? Awesome. Okay, so we could create another value in our pattern, and it would look something like this. That we would go with. Very good. So we're going to actually look at the numerical pattern of values that these dots represent. So if I looked at how many dots there are, there's 1 dot here. How many is in the second figure? 3. How about in the third figure? 6. The fourth figure? 10. And then 15 in the one we created that I didn't read. And if you take a look at those particular numbers, I'm kind of out of space. Let me try and make it smaller one more time. If you take a look at those particular numbers, and you look like we did at my earliest example today, the first one we started with, what would I have to add to 1 to get 3? 2, and to get to 6? 3, and to get to 10? 4, and to get to 15? 5, and visually you know why that happened. It's the new row you added at the bottom, right? Yeah, it's the new row you're adding at the bottom. But if you take a look then at those numbers, how much are you adding to get between those numbers? They're all 1s, aren't they? They are. So if you were asked if you were wanting to identify, this is actually a second differences, right? They have common second differences. So the numerical pattern of our dots, I didn't write it in the right spot, but it would have been 1, 3, 6, 10, 15. Those are triangular numbers. There's another type of numbers we're going to look at, figurate numbers anyway. They're square numbers. So again, we're going to start out with 1 dot. And then we're going to start out with this arrangement of dots. Wow, that was terrible. That's a little bit better. And then I'm going to do this arrangement of dots. And we'll do one more. Okie dokie. What would the next pattern of dots look like? A 5 by 5, right? It would look like 5 by 5. I'll draw it in. Okay, and what numerical pattern are we recognizing here? Well, this has 1 dot. What's next? 4, and then 9. There's a couple patterns you could recognize. What do you see? They're squares. So this one would actually be pretty easy to tell you that the general term is actually just n squared, right? It's squaring every term, so that's kind of cool. If you were looking at the pattern the way we did on the previous one, 1, 4, 9, 16, 25. How do you get from 1 to 4? With summations, like adding. Plus 3. How do you get from 4 to 9? 5. 9 to 16. And 16 to 25. 9. And of course, when you go between this pattern, what do you see? They're all plus 2, right? So these have again, a common second difference. The numerical pattern, of course, we've already written down, but I'll just write it in here. And then it is 1, 4, 9, 16, 25, and so forth. All right, one more example we're going to take a look at. I teach in the Hurley College of Science and Math. I like to think it should have said math and science, you know, because I teach math. It's kind of important stuff. We actually are a fairly young college. We're the youngest college on campus. Okay, so I don't know if you know that, but like the college that you guys are a part of is what? Do you know? What is it? What'd you say? I'm just not hearing you. Humanities and Social Sciences, right. It's Humanities and Social Sciences. I think it's even got somebody's name on it. The name on ours is Hurley. I think there's a name on yours as well. But it used to be that we were in the same college, you and I, so to speak. Okay. But in 2011, they split some of the divisions and stuff, and we got split apart to be the Hurley College of Science and Math. And our dean at the time actually wrote this on the board, 3, and then she put a dot, and she put 1, 4, 1, 5, and she asked, when we walked into our first meeting of the year, for us to write down the next 2 terms in the sequence of numbers. So I want you to do the same thing. I would like for you to write down what you would expect to be the next 2 terms in the sequence of numbers, and why. So write down what the next 2 terms should be, and why you think that's the case. Turn to a neighbor. Ask them what they think the numbers should be. See if you have the same expectation or different expectations. Okay, what do you think? What was your expectation? Give me a list of what you think. We don't all have to think the same thing. It's okay. What do we have? What? Okay, so I didn't know which numbers are you think.
Oh, 92.
You think 9, 2. All right, we'll get back to that. What else do people write down? 1, 6. Did anybody choose anything different than those 2? That was it? Okay. So if you chose 1, 6, how were you thinking about this problem? Okay, so you were looking at this as a pattern where the ones kept matching up, right? Every other number is a 1, and then the other terms, 4, 5, the next one would be 6. Everybody good with that? Okay, is that a legitimate way to look at this and suppose that the pattern is happening? Yes, it is. So, Ivana, am I saying it right?
Yeah.
Were you the one who said the 9-2?
Yeah.
Yeah. So, did anybody else think 9-2 over here too? Oh, several of you. Okay. So, if you were thinking 9-2, I heard your voice, so I'm gonna keep asking if you don't mind. Ivana, why were you thinking 9-2?
Because, I don't know, in high school you used a lot of 3.14, like they really just burned it into me. So every time I see 3.14, I'm like, it's pi.
Okay. So you looked at this and your mind automatically said, that's a shortened version of pi that's on that screen. What about others of you? Anything else that you'd like to add to that thought? Okay, so we're in this room with, I don't know, a dozen or so math and science people. So what do you think we all wrote down? We did. Every single one of us. In fact, we wrote it down and we all looked at each other and we're like, well, duh. Obviously, that's what it is. And in fact, those of you who wrote down 1-6 probably said the same thing. Well, duh. Obviously, that's what it is. Super easy pattern. I see it right away. So which answer's right? Well, it just depends, right? So the catch and the reason I always present this example is because I want you to understand that what we have done, no matter which answer choice you thought it was, is that we've done inductive reasoning. Okay, that's what we did. So what does this example show you about inductive reasoning? It's a great way of saying that. It doesn't necessarily lead to the same answer. So when I look something and I do some in my inductive reasoning, and Hannah looks at something and she does her inductive reasoning, we could both come to a legitimate, like how we thought about it, reason for our answer, and they could both be quote unquote right or acceptable or whatever and be different. Inductive reasoning is a little tricky like that, right? Patterns don't always lead to the same conclusion for everyone or in every situation.